Hello and welcome back to another episode of the Oxford Online Maths Club. My name's James and today I'm joined by Anjali.
Hi, my name is Anjali, and I'm a master's student in mathematical and theoretical physics at Oxford. And we are kind of going to talk about some physicsy and mathy stuff on today's stream.
That's
So
that's
happy
right.
to talk to you, James.
Thanks for joining in with the stream today. We've got a kind of quantum topic going on, so hopefully we'll do some sort of physicsy sort of stuff as well as some maths. Good to see people. If you want to join in live, my square is at the top, Angela is underneath, and then underneath could be you. Because if you're watching live, you could join in at slido.com/OOMC, or if you go to slido.com and put in the event code OOMC, that stands for Oxford Online Maths Club, then you can join in with this live chat like Aaron has. Aaron says, "Hey everyone." And an anonymous person says hello to both of us. Hello, anonymous person. You are a good reminder that in Slido you can be anonymous and we won't know who you are. You can put a name in there if you want to, but we won't know if it's your real name. Chat is moderated. The rules are please don't swear and please don't divide by zero. But we're going to play along nicely. That's also where we run things like a poll. Actually, I always do this poll to ask them how their day's going. It's a 5-star scale. On a scale from 1 to 5, how is your day today? I could ask you as well, how's your day going on a scale from 1 to 5?
I think mine is quite a solid 5. I think the weather definitely adds to that. It's been sunny today, and I've had a good lecture, nothing too hectic.
Oh,
Yes.
very nice. I
What
thought you
about
were
you?
almost about to say -5, but not quite. No, mine is quite good today as well. The weather's got much nicer around here. For people watching the recording, at the time that we're live, it's February, and it's a surprisingly not February day at the moment, or at least it is when you look at it through the window with a cup of tea. Chat's having an okay day, I'd say. They voted. Uh, 4.5 stars, more or less. There's a bar chart. I'm always looking out for people who are having a terrible day. I guess today maybe their day is so terrible that they haven't clicked on Maths Club. Right, there is a starter question on the screen as well. If you are saying hello or joining in with the polling, the starter question on screen here is: I'd like to know for which values of k is sine kx the same function as sine k, and then in brackets, x plus 360 degrees. If you prefer radians, then you can pretend that says 2 pi radians. So I'd like to know, I guess that's a translation, so I'd like to know if you translate sine kx, do you get the same function? Is it obvious what I mean by same function?
Yeah.
I haven't tested this one question or anything. Can you tell me what you think I mean by same
Um,
function?
so the nature of the graph is the same, like it takes the same values basically.
Yeah, nice. Okay, yeah. I was going for same values when you put in a value of x.
Right.
Good. Chat is coming. It's coming down to a 4.5. So I'm going to turn off the poll before. Yeah, someone's having a 3-star day, which is in the middle. Let's see if we can get that up to 4 or 5. People in chat having a go. Hi, Mary, Kadame, and Aaron are having a go at the starter question. While you're having a go at the starter question, I don't mind if we get multiple answers to the starter question. I know everyone's sort of typing at the same time when it comes to this sort of thing. Standard adverts at the start. There's a sort of ad break at the start around here. There's a summer school called Promise Europe that's running in Oxford. It's a 6-week summer school full of loads of maths for people across Europe. If you're watching internationally, more internationally than Europe, there's another one of these in Boston and there's another one in India. But summer schools with lots of maths in. And if you're looking for the Maths Club, if you've somehow found us on YouTube without finding our homepage, then oh my goodness, we do loads of these, and you can get them at /r/club. So maths.ox.ac/r/club to get previous episodes and also a kind of blog where we put up further reading notes occasionally of things that we forgot to say or things that we said could be wrong. What other notes? Good. The plan is to talk about a bit of maths and a bit of physics. Did you already tell them what are so you're here for maths and theoretical physics on our master's program at the moment. I forgot. Did you already tell them what you were doing before? Do you want to say?
I did mention my master's, and I think today we're going to talk about a bit of quantum mechanics and in particular about the hydrogen atom. So, which is like a big problem when you first study quantum mechanics, right? It's the part where you get to like apply all the little things that you learn in the toy problems and you're solving Schrodinger's equation. So I'll
Yeah, we're going to try and do all of that. Ooh, in chat, can we know what the next session is going to be? Sometimes. Usually, so I put the video up the day before, so you can get a sneak preview of what the title is going to be the day before. But I'd be lying if I said I always had a plan for what next week's episode is. So no, little peek behind the curtain there. Don't always know what next week's going to be. I currently know roughly what next week's going to be, so that's good. Right, good. That's made me smile. Sorry. Right, votes in chat are kind of for maybe K has to be a whole number, or maybe any number. So you've got multiple votes on what's going on. I suppose if K equals 1, this is a good check perhaps, what's going on. If K equals 1, then this property is a kind of famous property of sine. The K's just become 1s, and this just says, is sine x the same function as sine of x plus 360? And yes, it is, right? That's just a property that a sine has. So this is kind of like good news. Whatever values of K you think the answer should be, it's got to include K equals 1. I'm very lazy. What sort of values could I check next? I guess that's an open-ended question. Depends how lazy I am, right? Any suggestions? Or...
I think we could check for a half integer value or...
Right, yeah. So let's check. Maybe it's the integers. So maybe we could check like K equals 1/2. That's like some thinking now. So I've got to work out whether sine of x over 2 is the same thing as sine of x over 2 plus 180. This is a question about, I guess, what's the period of that function? It's periodic because it's got sine up front. But what's the period? Oh, and chat is joining in as well. There was a question, can we request what we discuss next? Yes, there is a contact email address on the Maths Club homepage. If you can find the Maths Club homepage. If you can find the Maths Club homepage on screen somewhere or in the YouTube description, there's an email address to suggest topics. I've just got a warning note from YouTube that says my computer's doing too much stuff. So sorry if we've suddenly become very jerky. But chat's also suggesting 0 and -1, which I think are easier to check. The thing about the integers is that they're just easier, right? So 0 works, -1 works because it just flips both of these functions. I think if K works, then putting negative that number in is going to be good. So I'm still happy that it might be the integers. After loads of thinking, I think it's not true that that one works. I don't know, is that obvious or am I off base? What do you think, Jelly?
I think like to get a general solution, maybe expand the sine of a plus b thing.
Ooh, that's cool.
Yeah.
So if you know a rule about sine of a plus b, then you could write this one as sine kx, and still inside the brackets, kx plus 360 k.
Yep.
And then maybe that'll be the same thing as sine kx when the dust settles, if you expand it out, or maybe not. If you don't know what I'm talking about, it's because maybe you haven't learned yet. There's a rule for expanding sine of a plus b into things to do with sine a and cos b, things like that. Yes. So if k is a half, then this is asking about sine kx plus 180 degrees in here.
Right.
So I guess the question is it true that the graph of sine x over 2 shifted by 180 degrees, so they get you back to the same point? I think no, because the period of...
I don't think so because, yeah, it will shrink.
Oh, my computer is really not happy. I'm going to try and write less, see if that helps. Oh, I could also close some tabs, couldn't I? That'd be a good idea. Yeah, so sine does repeat every 360 degrees. So if k is an integer, then we're kind of done, aren't we? That's a good point. Because if k is an integer, then shifting it by 360 degrees times k means shifting it by 360 k many times. So that'll be good. Yeah, okay. I think that solves it for integers. For k not an integer, I'm not sure I'm 100% convinced. But chat is going for it. Okay, I'm going to leave chat a second here. This is fun. I wasn't really sure. I haven't tested this question on anyone. So I wasn't sure if it was going to be the sort of thing where everyone just says, it's obvious, it's just obviously the integers, or whether we could have a discussion about it. And it's the latter, which is the good one. Yeah. Yeah, so one way round is easier than the other. What I mean by that is convincing me that integers work is, I think, not too bad. Convincing me that nothing else works is quite a bit harder.
Right. I think actually drawing the sine curve for non-integer values would help.
Yeah, when you shift it 360 degrees, is that like a whole number of the periods of the sine curve? I'm trying to draw less because it's making my computer sad.
Oops.
I'll do one sine wave. So if you know about wavelength, perhaps from physics, then you might have some ideas about what this distance is, and you might have some ideas about whether shifting by 360 degrees is a whole number of those waves. I think that makes it work. Good. Okay. I'm going to call that a solution, more or less. Chat's still having a go. I think testing on the person I've got on Zoom. How convinced are you right now that it's integers? That's whole numbers.
Yeah, I'm very convinced.
Good. Okay, brill. You were already convinced though, maybe. And then I've done some messing around that hasn't. No, you convinced me. Right. Okay, even better. Good. Right. That's the theme of today. The theme is quantization. So if you take away nothing else from today, then here's a new word. I've spelled it with a Z to be all American, but then I've said Z to be all British. Today we're learning about quantization, which, roughly speaking, is when the answer to your problem turns out to be integers, like whole numbers. A problem where it could have been any of the real numbers, but oh no, it turns out to be the whole numbers. Do you want to foreshadow the kind of idea in physics about... Do you want to say anything about physics and quantization? Where does this come up?
Absolutely. So I think we can compare classical mechanics and quantum mechanics. So classical mechanics is basically at the scale of things that we can see. So the basic idea behind Newtonian mechanics is you throw a ball and you can predict how it's going to move ahead if you know like the initial position, momentum, etc. But if you kind of go with the same thing for tiny particles, you cannot really predict how they are going to move. Or like rather, if we predict the motion of tiny particles using Newtonian mechanics, it doesn't seem to work or verify with the experimental stuff. And what comes up when we do experiments with tiny particles is that, for instance, the electrons in atoms only can occupy a certain orbital, so to say, or that is basically a kind of quantization that it cannot be in between, but rather only at these particular steps. So that is somehow quantizing um, your position for an electron. And that is an example of like quantum mechanics and how that comes about in physics.
And it's those orbitals that I want to try and get to today. I think this might be a bit ambitious, but I'm going to try and do parts
Okay.
of parts of the maths that turn up when you solve the equations to work out the probability density function for where an electron might be. It's a really weird question, right? To say I've got an atom, and the thing that you might draw in like the emoji for an atom, for example, the one in the thumbnail for this video, the thing that people draw is like this kind of thing, right? With the
Right.
here are the electrons, around they go,
Yeah.
whizzing around in orbits like this. This isn't a very good model of reality somehow.
Mm.
Because in some sense these electrons are doing in the little squiggly picture, these electrons are doing classical orbits. They're just going around, maybe in circular or elliptical orbits around the atom.
Right.
The result you would get if that were the case would be that almost any energy level is allowed, because different energy would just correspond to a different radius of orbit. That you would have electrons of all sorts of continuously varying energy depending on where they are. A bit like how the planets orbiting around the sun have got some energy associated with that motion, but kind of could be anything as they move around the sun. That sounds reasonable until you look at the actual energy levels for atoms. I can't remember how this experiment works. Can you remember what you do to atoms?
I don't remember if this was the first experiment, but it was probably, I think, one of the spectroscopy. I don't exactly remember, but it was termed as the ultraviolet catastrophe, um, which was like the energy levels were only measured to be at certain levels. I can't exactly remember the entire background of that, but
Yeah.
uh,
How does the ultraviolet catastrophe work? Maybe that's one for the further reading notes. But it's something like you. Is it something like you blast the atom with some energetic photons or something, and see what happens? Maybe it'll absorb the energy of the photon, jump up to an excited state, and then later fall back down again. That's some sort of experiment you can do, I think. Hamish in chat is telling me about spectra from ionized noble gases, possibly the Bohr model. Yeah, okay, it's kind of well done, chat. Thanks. Maybe I should let chat talk to each other about physics. Carry on. Um, anyway, so it turns out that electrons in the real world don't work like that. They don't have these kind of continuously varying amounts of energy levels. They have discrete quantized integers for the energy levels. Okay. Integers up to the fact that their energies, they have units. There's some scale for how big. What does one mean for an energy level? There's some physical constants in there, which I'm sure we'll get into. But in relative to each other, integers. It's not too bad. It's pretty cool. Okay, let's try and do the ambitious bit. Hold on, everyone. I could just pull all the punches, but I kind of want to just show you what's going on. So we're going to try and do a bit of both. Here we go. The error message has gone away. Let us know in chat. I think we were probably really jerky and horrible for the last 10 minutes, but possibly it's got better, or maybe it's got worse. I don't know. Let us know. Right, okay. I've taken a screenshot of some lecture notes. Sorry if this gives you flashbacks to lecture notes. Sorry in chat if this gives you flash forwards to lecture notes you haven't seen yet. I stole this from second year of Oxford Maths. There's a quantum theory course in the second year of Oxford Maths. It's optional, but I think it's fun. So warning signs. What have we got here? We've got the three-dimensional stationary state Schrödinger equation for a potential V as a function of R. R here is, let's start from the inside. So we've got a potential V, oh my goodness. Got to explain what that is. We've got energy on the right hand side, E. We've got mass inside here, so mass of the electron. We've got this quantity H bar. Is that? Oh, right, okay. Pop quiz, sorry, I should have briefed you. Is that the Planck constant or is that the reduced Planck constant or something?
Planck's constant is h, and h bar is h over 2 pi.
Cool, so factors of 2 pi everywhere, 2 exclamation marks there. We're in 3D, so 3 exclamation marks. And we're trying to solve whatever on earth stationary state Schrödinger equation, which I think I'm just going to label as kind of physics. Broadly speaking. I should probably put some exclamation marks on Schrödinger as well, because I'm not an entirely pleasant person. I'll put something in the further reading notes. This is kind of what we're up to, though. Physics has given us some equation, which they say represents what's actually going on for electrons. Are they right or not? Who can say? At the moment, mystery. Trying not to cast us as maths versus physics too much, but part of the job sometimes for mathematicians is to say, well, can we solve stuff? And sometimes physicists might have ideas about models for the real world, and you might need all sorts of maths to actually try and solve for what's going on there. I really haven't said anything about most of the symbols on the screen, so I guess I'm just bamboozling chat with, hey look, all of these symbols. Thank you, Enora. Glad that streaming got better. Just after I said that, my computer threw me a different sort of error message, which might have ruined things in a different way. So I think I'm cursed. That's life, isn't it? Okay. My plan here is not really to dig too much into the details of what this means, except that big picture, there's some physical equation describing what's going on for the electrons in terms of, at the moment, some unknown energy. At the start of this game, we don't know the energy. Let's get an exclamation mark and a question mark. No pressure, Angeli, but do you want to go at explaining the fact that, so psi represents this kind of probability function or something related to the probability function?
Right.
Do you want to go at explaining that, or?
I can try. So psi is called the wave function, and the wave function basically describes any kind of physical system when we go to the quantum limit, just like how knowing position or momentum tells us everything about the particle in Newtonian picture. In classical picture, we say that understanding the wave function really tells us about what our system is doing. So psi is called the wave function, and mod psi squared gives us the probability amplitude, meaning if we integrate mod psi squared, that gives us the probability of finding the particle at that particular location. So psi basically represents the physical probability for a system to be in a particular state. Does that make sense?
Yeah, that was great, thank you. That would have been a disaster if I tried to do that bit. So we've got the Greek letter psi, which is used for this wave function.
Right.
And I've put it as roughly equal to on the screen. There's some relationship between the square of the absolute value of this thing, something to do with probability. Depending on how much statistics and probability people have done in school or equivalent, they might have seen probability density functions. This idea that if you don't know something, and it could be something from a range, continuous varying range, you might have some concept of, well, it's probably around here, but it could be slightly off. So you can maybe draw some sort of bell curve or something to say, I reckon it's around here somewhere, but I might be wrong. There's some variance to that. Or maybe you know it's either around here or around there. It doesn't have to be a bell curve. It could be something where there's something like, oh, it could be here or here. Not sure. It's a way of describing something uncertain. Say, I don't know. Okay. I wonder if anybody in chat is thinking. There might be one person in chat who is thinking this. So we've got to do it, I'm afraid. I've put mod signs around psi and squared it. And there's probably someone in chat who's thinking, you don't need mod signs if you're going to square it, because squares are always positive anyway. Do you want to surprise them with the kind of bad news?
So in general, when we deal with these wave functions, they are complex functions. And when we write mod psi squared, what we really mean is psi times the conjugate of psi. So if psi is given by a complex function, say a plus ib times x or whatever, we multiply it by psi star to get the probability amplitude.
Yeah, it's chat's favourite. It's complex numbers, which I really find it's really kind of incredible that you've got in this kind of worldview, you've got complex numbers flying around.
I know, right? It comes up so fundamentally and naturally everywhere in quantum mechanics, and that's beautiful.
Which is odd because you don't want the probabilities. You don't want the probability between complex numbers. No. You want the probability to be between 0 and 1, real numbers. So the probability corresponds to something to do with the magnitude of psi. If people have seen magnitude and argument for complex numbers, the magnitude is something kind of measurable, I think. It's kind of like real quantity that I can cling to. But the argument or the phase of the wave function is something totally alien that I'm not going to get any intuition for at all, because the phase or the argument of psi could be evolving and changing. The complex number could be rotating around in the arcant diagram, which wouldn't change the probability stuff, the kind of real measurable probability, but would be changing something. One person is thinking, and yes, so chat roughly 50-50. One person was thinking it, and one person kind of guessed that complex numbers might be involved. Complex numbers everywhere you look. Anonymous has just joined, and they say, what is this you're looking at? Right, hi. This is some advanced multivariable calculus to do with quantum mechanics. I've taken the questionable decision of just throwing it on the screen and putting exclamation marks and question marks all over it. This is, believe it or not, related to an idea in physics that describes reality, even though we've just found out that it involves complex numbers, it involves uncertainty about where stuff is or what state things are in, and it involves all of these weird constants, some of them involving 2 pi. Good. My ambition is not that people write all of that down and understand exactly what's going on in Schrodinger's equation, because the point I'm trying to make here is there's some horrible differential equation, some horrible equation that relates, oh my goodness, what's going on, and that contains information about how we think physics works in the quantum world, and how we think that interacts with a potential for how we're going to explain the potential. We can do this. The potential, like people might have heard about potential energy or gravitational potential, I suppose. Possibly they could extend that idea to the idea of some sort of electric potential, to say if you've got an electron and a proton, there's some sort of potential associated with how far away those things are. Is that fair enough?
I think so.
So it's kind of
Mm.
the endless battle, right? That for physics, it's really important to understand what that is and where it comes from. If you just want to solve the maths, then yep, it's a function. It's a function of r, and it's in the equation there. Okay.
Yeah, I
uh,
think potential energy by nature is something that arises because of the configuration of the system. So if we have a bunch of electrons in a certain configuration, and if we were to move around, how much energy would be required to move it from here to here?
right.
It is sort of how much potential energy does that system hold?
Sure.
I think
Okay.
that.
So I'm going to think of that as being a bit like gravitational potential, even though it's really some sort of electric, maybe quantum thing. Hamish asks a good question, which is why is it a differential equation? I said that by mistake. Now I'm going to have to. And that's because there's another symbol I haven't pointed at yet. Oh my goodness! It's this upside down triangle. The upside down triangle. Oh my goodness! Squared is the Laplacian operator. This is the good bit. So, been saving this. Um, in general, this thing with a 2 up here means a whole lot of derivatives of psi. Right. How much of this am I going to do? Not sure. So the notation is a little bit mad because it's upside down triangle and it's squared. This symbol together, it's a thing. It's not something you really try to understand and think too deeply about, like what is a triangle and why is it squared. It's a shorthand for a whole bunch of derivatives. We've got three dimensions, so there are three sorts of derivative. My computer is really unhappy about this. These are all 2's. My computer is so unhappy about this. Okay, so bear with me. That's awful, James. I've done a really bad job there.
I think it's okay. I've gotten used to it after my lockdown online classes.
You can maybe even hear on my microphone the plane-like noise that my GPU is now making, which it is not happy about this quantum stuff. Poor little computer. Okay, so 2x derivatives, 2y derivatives, 2z derivatives, sum those up. I'm not going to explain partial differentiation right now on this stream, even though I've just written some partial differentiation on the screen. The idea is just, in general, psi might depend on the x direction, in which case I would like some x derivatives, please. Please differentiate it like a function of x. It might depend on the y direction, in which case I would like some y derivatives, please, 2 of those. And it might depend on the z direction, in which case I would like 2 derivatives in the z direction. So to cover all bases, I would like you to look at it. If it's a function of x, differentiate it twice with respect to x. If it's a function of y, differentiate it twice with respect to y. If it's a function of z, I'd like to differentiate it twice with a function of z. It's probably all of those things. Add them all together. That is a kind of combination of derivatives that you see quite often in maths. This is the good bit, I think. The process I've just described of do 2x derivatives, do 2y derivatives, and do 2z derivatives, and add them all together, that process turns up in loads of places. It's in the wave equation, for example, the one that you use for sound waves. So if you're studying oscillations in air pressure to explain how sound works, then you end up building a model that has those derivatives in it. 2x derivatives, 2y derivatives, 2z derivatives. Do you want to give another example? Have you seen this thing appear somewhere else? I've collected a bunch of these over time.
Mm, I was thinking of the same fluid motion.
Yeah.
That's where it comes up.
So it turns up in fluid dynamics in multiple places. This sort of thing is behind the shapes of water waves, but also, well, just loads of things like the derivatives turn up in the Navier-Stokes equations behind fluid dynamics. It's also in the equations for so Maxwell's equations for how electromagnetism works, which includes light waves, electric fields, and magnetic fields.
Right.
And it also turns up in the Schrödinger equation for quantum mechanics. So there's something important about this Laplacian operator, which is 2x derivatives, 2y derivatives, 2z derivatives. Yes. Anyway, that's a mess, right? That's too many things for anyone to keep track of.
Mm.
Somebody in chat has said this seems pretty different to A-level maths, and yes, I'm aware. This is the sort of stuff that you might get into at university if you do a maths or physics degree or something like that. That you meet maybe quite early on. I don't know how soon you'd learn it in physics, but sort of this sort of like doing derivatives with respect to different directions. So if you've got a function that depends on x and y and z, you do
Right.
derivatives with respect to this.
Yeah, it comes up in electromagnetism, I think, when you try to solve for different kinds of configurations. I think finding potential energies and stuff for.
Yeah. So there's a bunch of different kind of physical equations where you might come across this sort of maths. In maths degrees, the ones I've seen, we tend to teach it first. So you learn about this first, like watch out, this thing is out there. Let's study it and understand what's going on. So we might spend a chunk of first year trying to understand this thing, and then in second year we can let students loose on, go and understand quantum mechanics or something. Good. Okay. Joe says very unhappy, haha, possibly meaning my computer, which Joe can hear. It just calmed down a bit, but now I'm going to move the screen. Okay, so we've got a lot going on. I suppose nobody came to the stream, nobody clicked on quantum waves thinking that sounds easy. So surprise, it's really not. My plan is that in 3 dimensions, I can tell you 3 slightly different stories about quantization, about the way you get the problem splits down into integers. And we'll get 3 integers as a result of those 3 stories. I think I want to do this quite quickly because once we've got the integers, there's an interesting relationship between them that helps us understand chemistry as well. Somebody at
Okay.
home, yeah, gonna go. Now that I've said that out loud, it sounds way too ambitious. Great news, everyone. I'm going to try and talk quickly so that we can also do chemistry. I'm going to do it anyway. Let's go. Okay. Side note, we're going to learn about a way to describe where stuff is in 3 dimensions. X, Y, Z is okay, especially if you have a kind of square tank full of fluid dynamics. Been there, done that. But if you don't have a square tank full of fluid dynamics, then you might want to use a different way of describing where stuff is. So for the hydrogen atom, where we don't have this kind of like square grid, we might want something a bit more spherical. So this is good because this is worth knowing whether or not you care about quantum mechanics. I don't know if people have met these before, but there's this alternative way of describing where stuff is, to do with spheres. One sphere pictured on screen. Okay, right. So let me know in chat, I think. Have you heard of latitude and longitude? I can explain them, I think. I've practiced. Broadly speaking, latitude is a little bit like where you are relative to the equator. Are you near the equator or are you near the poles? So lines of constant latitude are these yellow lines that go around the world. And longitude are lines that go from pole to pole. And if you change your longitude, you're changing where you are on that journey around the world. Ah, yeah, brilliant. People have done geography, great. I did wonder, have I overloaded this? The error message, by the way. The error message that I'm getting says overloaded, and also during the stream I've realised, oh no, I'm putting geography in as well. If you're watching at home and you also have an overloaded error, then don't worry, I think that's normal. Good, right, latitude and longitude, geography, let's go. This is quite a good idea. I'm not sure maths can claim this as an idea from like the ivory towers of somebody dreamed this up. I think this comes from the real world. Don't know if we would have invented it if we lived in space, but we happen to live right next to an enormous sphere, more or less. And humans being humans, we've invented ways for talking about where stuff is on spheres. This one, so I can talk about where I am based on how far up I am above the equator. So maybe I live here or something. We're about 55 degrees north, I think, in Oxford. Other places might be on different lines of latitude. And then for longitude, you've got to pick somewhere. And the convention for longitude is that 0 degrees goes through Greenwich in London. So let us know from chat if you're watching from Greenwich. 0 degrees represent. This also works for describing where stuff is even in a world without Greenwich, you'll be pleased to know. So even if you don't have Greenwich, you can pick an arbitrary direction. And go for that. And this gives you a way to use two angles to talk about where you are. So one of those might be the angle around this way. Oh, I've got colours for this. Let's use this one to say. So angles. This might be 0 degrees here, and then an angle going around this way might go up to 90 degrees at the pole, and it might come down to minus 90 degrees at the South Pole. That would be your angle for latitude. And then longitude, you might go around this way. I think I should use a blue arrow for this one. So as you journey around, you might have some angle going around that way. Okay. Here's where I'm going with this, which is maybe too ambitious, but we're going to get there. If you go out trying to solve the Schrödinger equation, the really complicated thing that we saw, you're looking for a function which, for physics reasons, gives you complex numbers on the output. But oh my goodness, let's not think about that. You're looking for a function that's just well defined and nicely behaved at all points in space. And you can think of that as being a function where if I give you latitude and longitude coordinates, I'm supposed to get an answer back again. Now the answer will be incomprehensible because it will be psi, a complex number with some correspondence to a probability density function, but oh my goodness, like it should be a function. So if I give you different latitudes and longitudes, looking around, if you like, on different points on the globe, or in different kind of directions, if you prefer, then I should get a function. Aha, chat is doing, is maths created or discovered? Opinions on stream? Created or discovered?
Both, maybe, in a way.
Oh, both, nice. Same question, but physics. Is physics invented or discovered?
Again, I would say both.
Again, both. Okay, same question, but music. Is music invented or discovered? People never do music. People always have, like, there's a set of topics where people just have strong opinions one way or the other, but you got to ask questions.
I think music was definitely created, and it is one of the best things I would say that's been created.
Yeah, but then you find out about harmonics. We did an episode about music a few weeks ago. You find out about harmonics. They're kind of just there because the harmonics are... Oh, the harmonics are precisely the thing we were talking about before. They're sine waves with integers in them. So those kind of just exist. They're kind of just like listening to the integers. So then I start to wonder whether those are... Never mind.
I will give that a thought. Yeah.
Chat, what else does it make on the spectrum of makes sense to ask the question versus doesn't make sense to ask the question? What else would you like to know? Whether it's invented or discovered? Ice cream. Is ice cream invented or discovered? Invented. Not a good question. All right. Good. Okay. Here's first sort of quantization. It's the latitude sort. So if I'm describing an orbital for where the electron is, then I need to make sure that when I go all the way round the circle and come back again to where I started, so if I go on a kind of around the world journey, around this way and back again, then I need to get the same value after I've done my 360-degree rotation, the same value again, because I'm now describing the same point in space after I've gone all the way round. So whatever these orbitals are, complex numbers, probability functions, whatever, when I go all the way round and get back again, I'm at the same point now, so I should do the same thing again. I think I said latitude where I meant longitude, but maybe I got away with it. I'm changing longitude as I go around. So if I change it by 360 degrees, I get back to the same point. This is precisely the question that we did at the start. This is the starter question. And it means that the orbitals, instead of just doing anything as you change longitude, they have to be periodic functions. So if you go all the way around, you get back again, and aha, we've got a periodic function. That introduces quantization for kind of the same reason that the problem at the start had integers in it. So in some sense, as a mathematician, when you see a problem like this that's periodic, you should expect some sort of quantization. There's some integers hiding in there. You get solutions like sine m times longitude. So as you go round, you get an integer there. That integer is called m traditionally. So m corresponding to longitude. And you see things like sine m, and I'm going to write theta for longitude. None of these conventions are important. Don't listen to me. Definitely don't write this down. But you see functions like sine m theta. Okay, first sort of quantization. Then when you go round, you should get back to where you started. Periodic functions. Turns out you get integers as a result of just asking the question of, can I have a periodic function, please? It's one sort of quantization. There's a second sort, which is once you've decided that, you can think about changing latitude to change as I move up towards the North Pole and down towards the South Pole. Do I get a nice function? And there's no repeating here. As you go to the North Pole, you get different points as if you go down to the South Pole. But there's a kind of different effect, which is all to do with what's going on as you get close to the North Pole and the South Pole. So depending on m, you get some solutions which are all very nice as you go round in the longitude sense. But if you continue that solution and work out, what's the consequences? What's going on elsewhere? The solution blows up and is horrible near the North Pole. The North Pole is really interesting in these coordinates because all of these blue lines all end up at the North Pole. And the orange lines get really small near the North Pole. So it's called a coordinate singularity. It's the reason why loads of maps are a bit weird near the North Pole. Considering doing a tangent about geography, I'm going to rein it in, I think. Do you know what I mean? Like you have a map and your map might be doing fine near the equator. But then near the North Pole, everything gets a bit stretchy.
Right, yeah.
The North Pole's just a weird place for your map because if you're doing like a rectangular map, north is up, then you kind of need all of the top to become the North Pole, which is just weird. The North Pole is like all of the top edge, perhaps. Depends how your map works.
If you kind of open up the circle, then the top line on the sheet is mapped to essentially a point on the sphere.
So on a map, the North Pole and Antarctica on your map tend to be enormous, even though
Right.
Antarctica's not that big. I mean, it's large, don't get me wrong, but it's not that big. And including the South Pole. The South Pole is just a point, but it's got stretched out to its whole edge. So the poles are weird. In order for your solution to behave near the North Pole and near the South Pole and not do something weird near the poles, because you're planning to roll it all up and have it as a single point, you get another sort of quantization that says your solutions only exist for some integer L, so some sort of latitude kind of thing. And you get these solutions. Am I going to get the functions right? No, I am not, but I'm going to try. I am starting to suspect that I'm going to get ML. So there's some weird solutions that happen in that direction, but they're quantized. They have to be certain solutions for certain values of L, integers, so that they're well behaved at the poles. I guess it wouldn't make sense for my function. If my function up here is supposed to be, all different values for different values of theta, then that's quite suspicious near the top, because all of these points with different values of theta going around and merrily around, they're all referring now to basically the same point. So, if you're planning to do different things in different directions, well, near the North Pole, those are all basically the same point. So you've got to behave yourself a bit to make sure that you have a sensible value over there. This is the challenge of writing down a function for the surface of the sphere. Yes, we've seen other sorts of maps as well. Good. So you do some horrible maths at this point to work out what these functions are and how they behave, and the surprise is that they are quantized as well. There's a second integer for people keeping track. We've thought about two different directions, two different dimensions, and we've recovered two integers. There is a third one to do with a third coordinate. I think I'd like chat to play along at home. This so far just describes a 2D surface, that's the one we live on, but or any other sphere. There's a third coordinate needed if I want to describe all of space. What's that third coordinate? Sorry, I've been talking loads. Do you want to answer the question or get involved on this way of? There's a third coordinate missing.
So we have the latitude, longitude for it's kind of the surface of the sphere. I would say for a solid sphere, you would also need a radius to tell how far you are from the center, right?
Yeah, brilliant. Yeah, if we go on a journey to the center of the Earth, then our latitude and longitude might stay the same if I drill directly downwards, although never dig straight down. But something's changing. It's the distance between me and my goal of the center of the Earth. So if I'm digging downwards, then I'm changing. People in chat saying radius or altitude, how close you are to the core. Yes, I like that one, Star. That one captures my mission. Or equally, if you launch a rocket and you go outwards from the surface of the Earth, then altitude is used to describe that kind of upwards direction. The other coordinate that people use is r. So people use theta for longitude, phi for latitude. I'm getting cold feet about that one. Sometimes people do them the other way around. And r is the third one for a kind of radius out from the origin. Nice. The story for this one turns out to be really weird. Let me tell you a story about this one that leads to an integer n. So we have kind of coordinates. Come on, okay, I'll use typing. My computer has almost had enough of me. Coordinates. Over this side. The story for the radial one is maybe you've set up a lovely function on the surface of the sphere, but actually you're supposed to be describing what's going on for this function psi at all points in space. I think this is the thing, right? Like you remind me. Sorry. So it's like probabilities, and maybe it's close or maybe it's far away. Is that? I've sort of lost track of the context. Can you remind me that what we're doing?
Um, so we wanted to find the expression for energy, right?
Yeah.
And the solution to the differential equation psi. So psi is going to be a function of r, theta, and phi, these spherical coordinates, right? And mod psi squared gives you the probability of finding the electron at that location in the atom.
Yeah. So quantum uncertainty, I guess, means that it doesn't have to do a circular orbit where it stays at a fixed radius. You might find it when you measure. You might find it closer to the origin or further away. It might be doing all sorts
Right.
of stuff. Which
So it's uncertainty within some limit, so you can find it in sort of a diffused region around that particular point.
exactly. So depending on the solution, the thing we're trying to find, that will describe, I suppose, are we likely to find it very near the origin, very far away?
Yeah.
I guess people sometimes draw pictures of these shells where they're thinking about, in chemistry, I think I saw some, you draw the nucleus at the middle and then you draw rings, these kind of shells.
Right.
And that's a little bit misleading because the shells they're not distance from the origin. Each individual shell contains some orbitals. Each of those orbitals has some probability distribution for radius, which is really complicated. Also, it's not just depending on radius, it depends on latitude and longitude as well. Madness. Anyway, I had a question for this. I think we're going to skip this for time. I'll put it in the further reading notes or something. The story here is that for your solution to be well behaved, you want it to be, once you've done some work to a differential equation, you want it to be well behaved at the origin. The origin now meaning like the middle of the coordinate system, and you also want to be well behaved out at infinity. So as you go out to infinity, it's not the case that the probability gets larger and larger as you go away.
Yeah.
That wouldn't make sense because it's got to be somewhere. Well, these probabilities have got to add up to 1. So it's sort of unbounded and growing really quickly, then that doesn't mean anything. Complex numbers are one thing, but we've got to add up. Our probabilities have got to add up to 1. So I'll put this and some discussion about this in the further reading notes. But there's some really interesting maths to analyse what's going on with the solution, even if you can't quite solve the equation, to go and find some form of the solution. Anyway, right. So punchline for that dimension is because you want to behave at the origin and behave far away for probability reasons, there's another integer. And at the end here, I've got a question that chat can definitely join in with. At the end, there's a positive integer n, which is something to do, so large N, which is something to do with the energy. I think the energy level is proportional to 1 over this thing squared at the end of the day. The solution that we found with all of these integers is 1 over n squared. Yeah. The solution that we found with all of these integers corresponds to having some sort of big solution with these integers little n and l and m for a given energy level, and this has got something to do with energy related to the energy that we started with, and basically every physical constant going. There's like loads of numbers in there measuring like how big is 1, what does 1 mean, and the idea is you want little l n plus little l plus 1. That's something to do with your energy, and m, the one for going around, has some limits to it. So you've got some freedom. You've got this question then about how many solutions are there. So solutions now, after all of the differential equations, all of the weird thinking about how it depends as you go round, how it depends as you go in and out, have boiled down to the solution is totally characterised by three whole numbers, N, L, M. I don't know why they're those three integers, but there you are. So we can do questions like this for, if I tell you that I'm interested in big N equal to 1, how many solutions can you find with whole numbers N, L, and M? I think not very many, so I'll give chat a second. Just in case it's the notation, integers here means whole numbers, could be positive, negative, or 0. And we are almost at some chemistry, which is home time. I'm going to overrun very slightly, I think. I can't tell if this question makes sense. No one in chat is answering it, so I'm going to assume I'm not making sense, and I'm going to talk to Angeli on stream. Hello.
Yeah, I think if capital N has to be 1, then N and like small n and L would have to be 0, right?
Oh, bother, I haven't told you that that's a positive number. Yeah, this doesn't work, does it? Because they can be positive and negative. This is why no one's answering. My question doesn't work. Bother.
Okay,
Right,
so
okay, drop this.
okay.
Drop this, I'll put a fixed version. I'll put a fixed version in. Right, okay. I'll put a fixed version in the further reading notes. Plus that mysterious link to the periodic table. Right, good. It was right here. It was right here. With a quick look at the orbitals for what do these things look like. So it's kind of weird. It's really hard trying to illustrate these things. I'll link to a couple of things in the further reading notes. But these solutions depend on theta and phi, these kind of variables that we've got going on here, for the kind of behavior around in coordinate space. And they also depend radially, which is impossible to illustrate in this because we're trying to show some function of 3 variables, and you can't colour in every element of 3D space.
Okay.
Sort of mess. This thing is triangular shaped, but if you really squint, the periodic table is kind of a little bit triangular as well. We will put something in the further reading notes relating together. Having more electrons filling up these energy levels is how the periodic table works. So if you understand the energy levels of these different orbitals, then understanding how many solutions there are, how many different orbitals there are, tells you how many elements to expect. So quick ad for the further reading, I suppose. We'll put something in there to explain, once you've got these solutions for different whole numbers, if you understand orbitals, you understand elements. Good, right, okay, I'm going to wrap up there, I think. It's not quite, no, okay, so fine, it's not even very slightly triangular. I'm getting flack in chat. Fair enough. Right, I've got my work cut out in the further reading, I think. Angeli, thank you very much for joining in with live stream stuff and doing all the physics interpretation along the way. Do you want to advertise anything at the end, or? Okay, cool. So people can find out more about physics at Oxford. Let's do a plug for physics, why not? Physics at Oxford are physics.ox.ac.uk, including the physics degree and perhaps the Masters in Maths and Theoretical Physics, which is a master's course that we do here as well. Thank you very much for watching possibly the most ambitious Maths Club episode we've ever done. Thanks for taking part, Angeli.
My pleasure.
We're going to be back in 167 hours for another episode, possibly doing things with differential equations. So the bit I've skipped where we talk about like what's going on with the differential equation and what does it mean to solve for, and what do you do if you can't quite solve it? Can you do any maths anyway? We'll try and do some of that next week. But until then, have a nice evening, have a nice weekend, and we'll see you next week for another episode of the Oxford Online Maths Club. Bye.
Bye.